Hi everyone, good morning, and I hope you're having a good day. In this section, we're going to talk about beats and then the Doppler effect. So let's start out with beats. Generally, when two sounds of different frequency are played together, you can hear two distinct tones. However, something interesting happens when those sounds are very close in frequency, around maybe a difference of 0 to 5 hertz. What can happen is that instead of hearing two different distinct tones, you'll hear a single frequency that's modulated. So its amplitude varies from between high and low amplitude. So you'll hear this one sound where its loudness is varying. And this creates a distinct pattern called beats. Okay, let's now look at the theory for beats. And to do this, let's consider two sound sources with these two wave functions, y1 at x and t and y2 at x and t, as we've seen before. And what I'm about to do is true for any conditions, but let's simplify and assume the following since it won't change the result, but it will simplify the math greatly. So first, the two waves have the same amplitude. Secondly, the sound detector is located at the origin, x equals 0. And 3, the two sources are in phase at phi1 equals phi2 equals pi. Okay, so when we do that, then at x equals 0, we have y1 at x and t, or just y at t, equals a sine negative omega 1t plus pi, and y2 is a sine negative omega 2t plus pi. Okay, so then this is a sine omega 1t, and this is equal to a sine omega 2t. And why we can do that is because sine of theta equals sine of pi minus theta. So that's a property of the sine function, so we can simplify that there. Okay, so if we write the net displacement, we're going to add up these two displacement functions, y1 and y2. So we have a sine omega 1t plus a sine omega 2t. And then we can use this trig identity, sine alpha plus sine beta equals 2 cos 1/2 alpha minus beta sine 1/2 alpha plus beta. And so applying that here, we have omega 1t and omega 2t, which are our alpha and beta. So that leaves us with 2a cos 1/2 omega 1 minus omega 2t, and sine 1/2 omega 1 plus omega 2t. And this is the wave function for the resulting displacement that produces the beats pattern. Okay, so this wave function has some interesting implications. Here, this quantity, 1/2 omega 1 minus omega 2, is called the modulation frequency, and 1/2 omega 1 plus omega 2 is the average frequency, or the average angular frequency. I've written that again here. So the frequency of the sound that's heard will be 1/2 of the two frequencies combined, so very similar to the original frequency. This new part is this modulation frequency. It doesn't matter which is higher, which is lower, so we have the absolute value here. It's 1/2 omega 1 minus omega 2, and it gives the modulation frequency, or the modulation angular frequency. So what's happening is now we're hearing a single tone when these frequencies are very close, and the amplitude will oscillate in this modulation envelope. So it varies between a loud and a soft sound as the amplitude changes, and this is due to the two sound waves interfering with constructive and destructive interference. So what will happen is this alternating loud and soft sound will rise and fall twice within one modulation period. So each time the sound rises and falls, that's called a beat. And if we want to find the beat frequency, then we need twice the modulation frequency. And before we had the angular frequency, so we can plug in omega over 2 pi, And so that's 2 times a half the absolute value of omega 1 minus omega 2 over 2 pi. And this 2 and the 1/2 will cancel, and then I want to move that 2 pi to each term so that we can replace omega over 2 pi with the frequency. So we end up with the beat frequency is F1 minus F2. So this is our important result here. F beat equals F1 minus F2. And that will give us the number of beats that we hear per second due to the interference of these two frequencies. Example 7, a piano string is supposed to vibrate at 132 Hz. A piano tuner strikes a properly tuned string and an untuned string and hears 3 beats every 2 seconds when the two are played together. A, at what frequency is the untuned string vibrating? B, what would happen to the beat frequency if the tuner increased the tension in the untuned string? Okay, so we're given some information here. We have one frequency of the string that's tuned correctly, and I'm going to call that F2. You could call it F1, it doesn't really matter. It's 132 Hz. And we want to use the beat frequency to find the unknown frequency F1. So then we can find the beat frequency because we know that there are 3 beats every 2 seconds. So that's 1.5 Hz. Now to solve for F1 here, we need to remove those absolute value signs, and we can do that by adding plus or minus on one of the two sides. So I'll put it on F beat. So then we get F1 equals F2 plus or minus F beat. So we're going to have two options here for that untuned string. We have F1 equals 132 Hz plus 1.5 Hz, 133.5 Hz, or 132 Hz minus 1.5 Hz, which is 130.5 Hz. And without any more information, there's no way to determine which one of those frequencies it is. There's two possible solutions here. Okay, let's look at part B. What would happen to the beat frequency if the tuner increased the tension in the untuned string? Well, we know from the wave speed equation that the frequency is proportional to the root of tension. We've seen that before. So if we increase the tension, then we'll increase the frequency of the untuned string. And depending on which frequency that was, it will have a different effect on the beat frequency. So F2 was the known frequency of 132 Hz. And let's look at the first case. If F1 is 133.5 Hz, if we increase that, then it's going to move further away from 132. So this difference will get larger and will increase the beat frequency. However, if we have the other option where F1 is 130.5 Hz, then if we increase that frequency, it will become closer to 132 Hz and will decrease that difference and decrease the beat frequency. Okay, let's move on to the Doppler effect. So the Doppler effect occurs due to relative motion between the source of a sound and the observer or the receiver. An example is the change in pitch of the siren of an ambulance as it drives past you, or a car honking its horn as it drives past you or you drive past it. We're naturally used to hearing these sounds that incorporate the Doppler effect. So the technical definition is here. It's the change in frequency of the sound emitted by a source as perceived by an observer when there is relative motion between the source and the observer. Basically why this happens is because if you picture these waves, as the source and the observer move towards each other, the waves essentially kind of bunch up and then the frequency perceived is higher. And then as they're moving away from each other, they spread apart and the frequency perceived is lower. So an example using water waves is if someone was splashing in a pool and making continuous waves and you were stationary, you would perceive one frequency of those waves. Then if you start to kind of swim towards those waves, you would collide with those wave fronts at a higher rate or a higher frequency than if you were stationary. So you would perceive that frequency to be higher. And if you imagine swimming away from that wave source, then there would be more time between wave fronts as you interacted or collided with them. To start, we'll consider two cases, either a moving listener or observer and a stationary source, and then a moving source and a stationary observer. Okay, let's first consider the case where we have a moving observer and a stationary sound source. So some definitions here. We have F naught, which is the frequency emitted by the source. VO, this is actually an O compared to a 0, which is the speed of the observer. I'm matching the notation of the textbook here. And then V is the wave speed. Usually this is in air, but we could talk about the Doppler effect in another medium. Okay, so the wavelength of the sound, just from V equals lambda F, is lambda equals V, the speed in air, or the speed of the waves, over F naught, the frequency emitted by the source. So if we're considering this case, let's look first at when the observer is approaching the source. If the observer is approaching the source, we'll eventually experience a higher frequency, or the observer will hear a higher frequency. And this is because it appears that the sound is moving faster than its speed in the medium. So the new speed is V plus VO over lambda, and then we can plug in for the wavelength here. So this is V plus VO over V F naught, since I've inverted this here. And then just rearranging, we get the frequency F plus equals 1 plus VO over V F naught for an observer approaching a source. So we can see from that formula that it will be higher as we expect. So the observer will perceive a higher Doppler frequency. And then if we were to say the observer moving away, F minus, I could have repeated this, but it would experience a lower speed. So instead we'd have V minus V naught here, and we would end up with 1 minus V naught over V, FO, for the observer receding or moving away from the source. So in this first case, we're going to get a higher frequency, and then moving away, the observer would perceive a lower sound frequency. Okay, now let's consider the moving source and the stationary observer case, case 2. We need one more definition here. Vs is the speed of the sound source. And okay, in one period, the wave moves delta x equals Vt, the speed of sound in the air, or V times the period, since that's the time in one period. I'm doing this because when the actual source is moving, that can be perceived as a change in wavelength of the sound. So we want to find the distance that that wave appears to move in one cycle. So the source moves delta xs equals V source t, or V source times the period. So the distance moved in one period has to be one perceived wavelength. So we can subtract these. The perceived wavelength, I'm going to consider first the approaching case again, is delta x of the wave minus delta x of the source. So Vt minus Vst, or V minus Vs times the period. Okay, so we have this perceived wavelength. We can plug that into our wave speed equation to find the perceived frequency for the approaching case. V over lambda plus is V over V minus Vs times the period, and then I'm just going to plug in period as 1 over frequency, our initial or frequency emitted from the source, which is F naught. So simplifying, this gives us two equations here. When the source is approaching the observer, we have F naught over 1 minus Vs over V. And notice that this negative is in the denominator, so this would give a higher frequency, a higher perceived frequency as we'd expect. And then I could have repeated all of this for the receding source. We would have had a positive sign then to increase the distance between peaks, or increase the wavelength. And we'd end up with F naught over 1 plus Vs minus V which is a lower frequency when the source is receding. I've just written again the formula here so you can see that we can combine all of this into one formula, and I'll talk about the signs for this in a second. Okay, let's put all of this together in one equation that also accounts for both the source and the observer moving at the same time. So we have f plus or minus, which just indicates the perceived frequency by the observer, or the Doppler frequency, equals f naught. So I'm going with the notation from the textbook in case anyone's using that. So f naught here is the source frequency. Then we have v, which is the speed of sound. Usually this is in air, but in whatever medium that the sound's traveling in. So the speed of sound, and then vo here, this is o opposed to naught, and it means the speed of the observer. And then vs is the speed of the source. So this encompasses everything that we've looked at so far, and we just need to be careful about assigning the signs. So you can do this just based on the knowledge that we need the frequency to increase when the observer is approaching the source, or when the source is approaching the observer. So in the approaching case, we would choose the upper signs. So the positive here will make this frequency larger, and the negative in the denominator will make that frequency larger. So the upper signs are for either source or observer approaching the other. And if both are approaching, we choose both of those upper signs. Then the lower signs are in the case that the observer or the source are moving away from each other. In that case, we'll have a lower frequency, and to get the lower Doppler frequency, we want a negative sign in the top and a positive sign in the denominator. So that's why we choose those lower signs. Now you can mix and match. If you have the observer moving towards the source, we choose positive, and then if at the same time the source is moving away from the observer, you could choose the positive in the denominator as well. If that's confusing, another way to do the signs is to assign a positive direction from O to S. So it has to be from O to S, observer to source, and then that's your positive direction. And then you could assign a sign for the observer or the source based on whether they're moving in that direction or against the positive direction. So on their own, these are speeds, and then just make sure to add the signs in the correct place. Example 8, a block with a speaker bolted to it is connected to a spring with spring constant 20 newtons per meter. The block and the speaker have a mass of 5 kilograms, and the system oscillates on a frictionless surface with A equals 0.5 meters. The speaker emits sound waves of frequency 440 hertz. Determine the highest and lowest frequencies heard by a person to the right of the speaker. Okay, first let's find the maximum speed of this mass on a spring or speaker on a spring in simple harmonic motion. So we'll need omega. It's root k over m. Root 20 newtons per meter over 5 kilograms gives us 2 radians per second. And why we need this is so that we can find the maximum speed. So it'll be omega a, which is 2 radians per second times 0.5 meters. So 1 meter per second. So the maximum frequency that's heard will be when we have this mass moving towards the observer at this maximum speed. So our two frequencies, f plus or minus for lowest and highest, will be f naught v over v minus plus vs, since we have a moving source this time and a stationary observer, so VO is 0. We know that this mass will move between Vmax and 0, or plus or minus Vmax and 0, and at 0 we will have that initial frequency of 440 hertz. So using Vmax will give us the highest frequency above that mean value, and then the lowest frequency below it. So F plus equals 440 hertz times 343 meters per second. The speed of sound in air, we can use the room temperature value over 343 meters per second minus 1. Choosing our upper sign here for the approaching case to give us the highest frequency, which is 441.3 hertz. And then to find the lowest, we have 440 hertz times 343 meters per second over 343 plus 1. And the lowest is 438.7 hertz. Move that up for a second. Example 9, a police car siren emits sinusoidal waves with a frequency of 300 hertz on a day when the speed of sound in air is 340 meters per second. The police car moves toward a warehouse at 30 meters per second. What frequency does the driver hear reflected from the warehouse? Okay, so I've written out the first step here. This is just one question, but I want to split it up into part A and B because we need to first find the frequency that reaches the warehouse. So treat the warehouse as the observer and the car as the source, and find the frequency at the warehouse, since that will then be reflected and perceived back by the car. So we have F naught is 300 hertz, speed of sound in air on this day is 340 meters per second, and then the speed of the source or the car to start is 30 meters per second. So we have a moving source and a stationary observer, so Vs here, and so I actually want negative. I'm missing my negative sign here. There, so V over V minus or plus Vs, and we're going to choose the negative sign. Two ways to think about this. One is to just choose it based on the approaching case, so we know the car is approaching the warehouse, and so we want that negative sign. Because we know the perceived frequency has to be higher, it's the upper sign, and it will give us the higher perceived frequency. So we have 340 meters per second times 300 hertz over 340 minus 30, which gives 329 hertz. Now the second way to think about this is the other way is to use a sign convention where we draw a line from O to S. So that would go this way, and that's our positive direction. And then we choose the sign for the speed based on whether it's in that positive direction or not. And in this case, it's opposite to the positive direction, so we get negative. So that's kind of systematic, and maybe if you prefer that method, you can use that. All right, so now we have the frequency that's reflecting off the warehouse. So in part B, we want to find the sound reflecting off this warehouse here. It's going to reflect here, and then arrive at the car. So now the car is O, and the warehouse is the source, which is S, and it's emitting this frequency from the warehouse. So now we want the sign still approaching. I'll use F plus, but we have a moving observer and a stationary source, so it will look like that. And instead of F naught, I'm going to write FW now, since it's as if our source is this frequency reflected off the warehouse. So I've chose plus again because it's approaching and I know that I need a higher frequency. Again, let's just check the O to S method. In this case, I would draw my line from O to S like that, and that's the positive direction, and the observer is moving in that positive direction, so we choose positive. Okay, so this is 340 meters per second plus 30 meters per second over 340 times 329 hertz. So we should get an even higher frequency of 358 hertz. I have a really good video about the Doppler effect that I usually show in class, so I'm going to put that below. And I would suggest watching it. It covers basically what I've shown here and then some applications of the Doppler effect. So we're talking about the Doppler effect for sound, but it also does apply to light. And with light, a change in frequency actually means a change in color. So the relative motion of the source and the observer for light could result in a change in color in visible light.